Okay, welcome back. Just a review of the gas laws that we started yesterday. Yesterday I discussed three gas laws: Boyles Law, Charles Law, and Guy-Lussac's Law. Boyles Law was looking at the relationship between pressure and volume, and it was an inverse relationship. So as your pressure increases, your volume decreases, and that makes sense. So if you take a look at this, I don't know, piston, cylinder, whatever, when we decrease the volume, air pressure increases because those gas molecules are colliding more with the surface of the container as well as with each other. Charles' law was looking at the relationship between volume and temperature. So here we have our molecules and we apply some heat and some greater heat, and over time our volume will increase because these air molecules, again, they're gaining average kinetic energy, so they're moving around faster. So as they move around faster, they're actually pushing against the surface of the container that they're in and increasing their volume. But obviously this container that they're in has to be flexible, kind of like a balloon, or maybe like a piston setup here. Guy-Lussac's law is looking at pressure and temperature. And again, that was also a directly proportional relationship, very similar to Charles' law, where if you increase your temperature, your pressure is going to increase, again, because of more collisions. Okay. Before I move on, I'm going to show you a really cheesy video that I made when I was student teaching up in the Arctic, and it's actually got some great demonstrations that you guys can do at home if you choose to. So enjoy.
Oh, hello. Previously, we've looked at gas pressure. Remember, pressure is a force applied to a specific area. One way you can increase pressure is by adding more gas. For example, a basketball. If you have a flat basketball, you can fill it up with air. The volume of the basketball doesn't change, but the gas pressure inside does. Now that we've recapped gas pressure, let's look at two laws that we will be working with in tomorrow's lab. The first law is called Boyles Law, and it deals with pressure and volume. Boyle discovered that the relationship between pressure and volume are always opposite and proportional. This is called an inverse proportion. As pressure increases, volume decreases. Think of it as a seesaw. As one goes up, the other goes down.
So there's the airline right there. Watch what happens to it. See how it automatically fills up, so it sinks.
Here you can see our bottle with the eyedropper in it. On the left-hand side, it's before pressure has been applied. But once pressure is applied, the eyedropper sinks because the volume inside the eyedropper holding the air decreases. Remember, inverse proportions. Let's say that pressure decreased by a fourth. Well, since it's an inverse proportion, this means the volume increased by a factor of 4. Notice my fractions on the bottom. Pressure decreased by a fourth, so the inverse proportion is when you flip them, meaning that volume increased by 4. The second law is called Charles' law. It deals with temperature and volume. I have a balloon here, right? And I've already measured the circumference of it, and it's about 23 inches. What I'm going to do is I'm going to place this balloon in the snow, come back to it about, 10-15 minutes later, and check to see what happens to it. Alright, here's my balloon. I'm going to take a close measure with it with the measuring tape. It's so cold that it's really hard to move it. Alright, so previously we were at 23. Now take a look at it. We're at 22 about Charles' law. So you just looked at Charles' law, which deals with temperature and pressure. As the temperature goes up, the pressure goes up. And vice versa. Temperature goes down, pressure goes down. Notice the drawing of the balloon at room temperature, it was at 23 degrees. After it was placed outside, the circumference was 22 inches. Charles' law, temperature and pressure, they are directly proportional. Meaning if temperature is increased by twice as much, your pressure is going to go up twice as much as well.
And I just realized that it probably should have been temperature and volume and not pressure, but they go hand in hand, Gay-Lussac's and Charles' Law. Okay, moving on to Avogadro's Law. So I'm going to talk about three more laws, gas laws today. Avogadro's Law, combined gas law, and the ideal gas law. Avogadro's Law is actually very simple. It's just saying that if you have equal volumes of gases at the same temperature and pressure, they have to contain the same numbers of molecules. So if I have 22.41 liters of argon at 0 degrees Celsius and 1 atm, which is standard temperature and pressure, the mass of that gas is going to be the molar mass of argon, found on the periodic table, 39.95 grams, which is 1 mole. So I have 1 mole of argon at this temperature and pressure if I have this volume. Same thing with oxygen gas, 22.41 liters of oxygen at standard temperature and pressure. The mass of it is 16 grams or 15.99, depending on how you look at it, which is going to be 1 mole of oxygen gas. So the volume of a gas is directly related to the number of moles, which just makes sense because if you increase more moles, which means more mass, your volume is going to go up, obviously. So that's all I want to talk about with Avogadro's. Moving on to combined gas laws. So combined gas laws, basically you're going to combine all three gas laws. You're going to combine Boyles, Charles, and Gay-Lussac's. And you can kind of see right here, pressure and volume and temperature all interrelated to each other. And this is the equation that you're going to use. Again, when you do temperature, the temperature has to be in Kelvin. So if you're given a sample problem of degrees Celsius, you need to make sure you do the conversions. Otherwise, you will get the wrong answer. So let's take a look at two sample problems dealing with the combined gas laws using the equation that's provided here. I'm going to move over to my whiteboard. So sample of gas at initial volume of 8.33 liters, an initial pressure of 1.82 atmospheres, and an initial temperature of 286 Kelvin simultaneously changes its temperature to 355 Kelvin and its volume to 5.72 liters. What's the final pressure of this gas? So you just plug it in and solve for your missing variable. So my ones are going to be my initial. Where did I start off with? So my initial volume of 8.33 liters. There's my volume. Initial pressure of 1.82 atms. Over the temperature. They gave it to me in Kelvin. That was very nice. 286 Kelvin. This has to be equivalent to our new conditions. So we have a temperature of 355 Kelvin. A volume of 5.72 liters. And we want to solve for our pressure. Okay, so let's just do all this. 1.82 times 8.33 divided by 286. You get a kind of a small number here. 0.053 atm times liter over Kelvin. Because we didn't cancel any units here, so we want to make sure we have them all. And then over on this side, we're going to multiply by 355, both sides. So, I'm going to squeeze that. Whoops, it's supposed to be 355. So, times 355 Kelvin equals P2 times 5.72 liters. All right, so 0.053 times 355, I get around 18.82. Now my Kelvin will cancel out, and I'm still left with atm times liters. So now we want to get pressure by itself by dividing both sides by 5.72 liters. The liters cancel out. I'm left with atms. And my answer, I'm just going to put it over here because of space, sorry. I get around 3.3 ATMs. Sorry, that got kind of messy because of space. All right, a little bit more space here. So remember my combined gas law is P1V1 over T1 equals P2V2 over T2. Okay, so here they just give it to me 662 torr, that's my pressure. My volume is 46.7 milliliters over temperature 266 Kelvin. My P2 is 409 torr. For solving for V2. And there's my temperature for the secondary conditions. So let's multiply and divide all this. I get 116.22 torr times milliliter over Kelvin. Okay, let's get rid of the Kelvin by multiplying both sides by 371. So 371 times 116.22, get a pretty large number. So Kelvin cancel out. Now I'm just got to get volume by itself by dividing both sides by 409 ATM. Oh, not ATM. Gosh darn it, guys. Torr. Sorry. Okay. So 43,118.84 divided by 409, I get roughly somewhere around 105.4 milliliters for my new volume. So there's the combined gas law. Now the last gas law I want to talk about is the ideal gas law. The ideal gas law combines Boyles, Charles, Gay-Lussac's, and Avogadro's, because now we're throwing in moles. I'm also going to throw in a constant, R. So the equation is PV equals nRT. Now, in order to use this value for R, your volume has to be in liters. So they give you something in milliliters, you have to convert to liters. Your pressure has to be in kilopascals. So if they give you atmospheres, torrs, PSI, whatever, you have to convert it to kilopascals. Moles is mole, and temperature always has to be in Kelvin. Okay, so let's take a look at a few sample problems using the ideal gas law. So my equation is PV equals nRT. So I'm just going to stick that here. All right, how many moles of gas in a balloon that has a volume of 15.9 liters? So there's my volume. Solving for moles, that's N, at a pressure of 149 kilopascals, so that goes over here. Son of a gun. 149 kilopascals. R is the constant, 8.314. Okay, and the unit for that is liters times kilopascals over moles and Kelvin. I went the wrong way. And then my temperature, oh, they give it to me in degrees Celsius. So I have 28 plus 273.15, and that will be in Kelvin. So let's clean this up. Let's multiply both of these. And let's see. 15.9 times 149, I get 2,369.1 kilopascals times liters. And then over here, 28 plus 273.15. So I'm going to add that together and then take that times the constant 8.314, and I get N 2,503.76. I don't know how far to go here. My unit is liters times kilopascal. This was Kelvin, so Kelvin's going to cancel out, and then I'm left with moles underneath. Okay, so I want to get N by itself, so I'm going to divide both sides by 2,503.76. Yep. And this is liters times kilopascal over moles. So my kilopascals and liters will cancel out, and I'm left with 0.94 moles equals N. Okay, another sample problem using the same equation, PV equals nRT. How many moles of ammonia is required to fill 14.88 liters? So there's my volume. With the pressure of 199 kilopascals. Solving for moles. I'm going to use my constant, 8.314 kilopascals times liters over moles times Kelvin. And my volume, 25 degrees Celsius. That means I got to convert it to Kelvin. I add in 273.15. This will be in Kelvin. So multiply these two together. I get 2,961.12 kilopascals times liters. Let's add these two together and multiply by the constant. 2,778.8. My Kelvin's going to cancel out, so I'm still in kilopascals times liters over mole. So now I want to get N by itself by dividing both sides by 2,778.8. Okay, 2,961.12 divided by 2,778.8. I get 1.06 moles equals N. Okay, last sample problem. This time they give me moles. At a pressure of 85.6 kilopascals. They want to know the volume, so we're solving for V. I'm going to use my constant. And the temperature, 26 Kelvin, or degrees Celsius, but I got to convert it to Kelvin. Okay, so let's multiply all three of these numbers together. Okay, so my Kelvin is going to cancel out, and my moles will cancel out. Okay, so I get 85.6 kilopascals times V equals 10,819 about my unit, kilopascal, times liters. So now I want to get V by itself by dividing both sides by 85.6 kilopascal. So that cancels. And I'm going to be left with units, or liters. Ow. So 126.39 liters. I think that's my cue. Okay, so I just went over the combined gas law, how it combines Boyles, Charles, and Gay-Lussac's to get this. And then I also just went over the ideal gas law that literally combines all the gas laws that we've kind of been going over with. So that's it.